Hello class! Topic 25 is on eigenvalues and eigenvectors. Now this is really a review topic for those students who have already taken linear algebra. If you have not yet taken linear algebra, then this will be new. I've devoted this entire topic to what these eigenvalues and eigenvectors are and how to find them. And then in subsequent topics, we will use them to help solve systems of linear systems of differential equations. Okay, so let's begin. Multiplying a matrix by a vector produces another vector. So matrix vector multiplication can be conceived as a functional operation that transforms one vector into another. Find the following products and then plot the input and output vectors. So we're going to consider this vector here to be the input vector, and it's going to be multiplied by this matrix. And the vector we get back, we'll call that the output vector. So matrix vector multiplication. The 2, 3, remember we bring them up here, and we drop them onto these entries, multiply corresponding entries and add, and then multiply corresponding entries and add. And that's how we produce our new vector. So this gives us 2 times 0 plus 1 times 3 for the first entry. And then the second entry will be 2 times 1 plus 0 times 3. Now this is a 2 by 1 result. I just got to simplify it. It looks kind of square, but it's not square. It's 2 by 1. It's not 2 by 2. And we get 3 in the upper position and 2 in the lower position. So multiplying, you might have surmised by looking at this, but if you multiply a 2 by 1 vector times this particular matrix, you will produce a 2 by 1 vector where the coordinates have reversed, where the entries have flip-flopped. It changes the order of the entries. So visually, there's a visual effect to this. If we start with a vector that's 2, 3, and think of that as the vector 2, 3 terminates right there. If it starts at the origin, a vector 2, 3 terminates right there. And when you multiply this vector by this matrix, it transforms into a new vector where the coordinates switch to the location 3, 2. There's 3, 2. Next example, we're going to multiply this matrix here by this vector. The vector 3, 1 we'll assume is the input vector. And this particular transformation, let's see what it does to that input vector. Okay, so the 3 and the 1 get brought up here, and then we're going to drop the 3 and 1 down onto these numbers, multiply and add. So that gives us the first entry will be 3 times -4, or -4 times 3, plus 1 times 6. And then when I drop the 3 and 1 down to the other two entries, multiply and add, we're going to get -3 times 3 plus 1 times 5. This is a 2 by 1 vector, and it simplifies to -12 plus 6 is -6, and -9 plus 5 is -4. So we began with the vector 3, 1, which is right here, and we wound up with the vector -6, -4. It might be harder in this case than in the first case to determine the general effect of multiplying vectors by this matrix. What happens to that vector exactly? In the case over here, it was pretty obvious, or if you do enough examples, you will see that it becomes pretty obvious that multiplying any vector by this matrix simply switches the two positions of the vector. The two entries of the vector will reverse. Now there exist these kinds of transformations that have very specific outcomes. Like there exist matrices such that when you multiply a vector to that matrix, it always has the effect of scaling that vector, like making it 5 times as long, or rotating the vector 30 degrees counterclockwise. There are a variety of matrix vector operations where the multiplying by the matrix will have a certain desired effect on the input vector to produce a certain output vector. Now let's keep this exact same matrix in our last example, but multiply it by 2, 1 instead and see what happens. So we do 2 times -4. 2 times -4 is going to be -8, and then plus 1 times 6. That's the top entry, the first entry, the 1, 1 position. Now the 2, 1 position will be 2 times -3 is -6, and then add that to 1 times 5. This is the resulting vector, and it simplifies to -2, -1. So when you plot both of these, the 2, 1 vector was right here. This was our input vector. And multiplying by this matrix 2, 1 was turned into negative 2, negative 1. Well, these two vectors, unlike the other examples, are collinear. The vectors point in opposite directions, but they do point along the same path, along the same line. That wasn't the case here. There was a slight bend, and certainly was not the case here. If you were to take the vector 4, 2 and multiply it by this matrix, you would get negative 4, negative 2. You would get the opposite of what we started with. In this case, multiplying by 2, 1 gave us the opposite of 2, 1. So you could factor out that negative and write it this way. But what's standing out here in this case is that there exists a matrix and a vector such that when you multiply the vector by that matrix, we got a multiple of that original vector. And this multiple was negative 1 times the original vector. Now that did not happen in the case where I chose 3, 1 as my initial vector. I did not get a multiple of 3, 1. Okay, moving to the next slide. The eigenvalue of a square matrix A is a non-zero constant R such that there exists a non-zero vector x called an eigenvector that satisfies the statement below. Now mind you, these x's are all bold. It can sometimes be hard to see that, but they are bold. They do represent vectors. So A is a square matrix times a column vector here. So this represents, when you multiply those, you're going to get a vector. And on the other side, we have a scalar times a vector. So on this side here will also be a column vector. So we have, this equation makes sense. We have a column vector on one side and a column vector on the other side. And they're the exact same vector according to the statement. If there exists a non-zero value r and corresponding non-zero vectors x such that this is a true statement, then we're going to call r an eigenvalue of the matrix A and x a corresponding eigenvector. So back in this context up here, we'd be able to call this matrix here as the matrix A. This would be an eigenvector, and the negative 1 would be a corresponding eigenvalue. And you can see the structure that we have here, where we had an ax, a vector x, turned out to be a negative 1 times the vector x. So this structure right here, negative 1 is the eigenvalue, and the corresponding 2, 1 vector is an eigenvector. Now, 4, 2 would also be an eigenvector of this. In fact, any multiple of 2, 1 is going to be an eigenvector for this corresponding to this exact same eigenvalue. We'll see that here in a moment. Okay, so once we have this statement is true for non-zero r and non-zero x, then we're going to come up with a way for finding all such values r and their corresponding values or vectors x for which this is true given any matrix A. So we're going to begin by subtracting rx from both sides. So now we have a difference of vectors here, and we have the 0 vector on this side. That's a bold 0. And then we can use the idea that a vector times, or an identity matrix times another matrix doesn't change it, right? If you take identity matrix and multiply it by a matrix, you're going to get that matrix back, provided the dimensions are all appropriate. Even if you multiply by a vector, you're going to get that vector back. Multiplying by the identity doesn't change anything. And so we can squeeze in the identity matrix right here in front of this x, because the identity matrix times x is the same thing as x. And the reason I'm doing that is so that I can factor x out and have an expression in the parentheses that still makes sense. For example, if the I wasn't written and all you saw in these parentheses was a minus r, this would be a nonsense operation because a is a matrix and r is a scalar. But if we have I in there, Ri is an identity matrix multiplied by r. Right, so if this is a 2 by 2 identity matrix, and when you multiply by r, it just winds up looking like this. You just have r's on the main diagonal. So this would be r times I. And it creates an operation here that is meaningful. It's a matrix minus a matrix. Okay, so what we're doing is we're trying to really figure out the values of r and the values of x, the vectors x, that make this statement true. And there's some theory from linear algebra that when you have a square matrix times a vector x, and you get the 0 vector back, if this matrix right here is invertible, or we use the word non-singular, then the only solution to this is going to be the 0 vector. So if you have an invertible matrix right here, and you want to multiply it by some vector to get the 0 vector back, the only way you can do that is to have the trivial solution of the 0 vector. But we're after non-zero eigenvectors here. So we want this equation right here to have solutions x that are non-zero. The only way that can happen is if the square matrix that's right here is singular, meaning not invertible, which means its determinant will be 0. So we want to find all values r where the determinant of this matrix right here will be 0. So remember, if you put a matrix in these absolute value bars, that means you're doing its determinant. You're finding its determinant. And we want the determinant of that square matrix to be 0. And the scalar is 0. So this is not the 0 vector anymore. This is a scalar. This last line here is called the characteristic equation. We solve it for r to find the eigenvalues of a square matrix. Okay, let's demonstrate this. Find the eigenvalues of the matrix below and confirm your answer with technology. Okay, what we do is we begin by setting up the determinant of A minus R times the equivalent identity matrix, equivalent sized identity matrix, and set this equal to 0. And this is a scalar 0, not a vector 0. So A is the matrix -4, -3, 6, 5. From that, we are going to subtract Ri of the same size. And Ri looks like R0, 0, R. Then we're going to find the determinant of that and set that equal to 0. Well, to subtract these, all you have to do now is subtract component-wise. Two matrices can be subtracted component-wise. And I'm going to, instead of putting brackets on my matrix, I'm just going to put the determinant notation. So it looks like absolute value bar. So bar, and then we do -4 minus r, that's the top left position. 6 minus 0 is the top right position. Bottom left position is -3 minus 0, so just -3. And then the bottom right position will be 5 minus r. So to go from this point to this point, all you notice is that you just remove r from the main diagonal. The other entries you keep the same. And then you calculate the determinant. So we still have this is equal to 0. And we have a 2 by 2 matrix whose determinant I'm after. So you got to multiply these entries here. So we get -4 minus r times 5 minus r. And then we subtract this product. So we do minus -18. So this will be plus 18. And this is equal to 0. Now we want to continue to solve for r. So I'm going to go ahead and distribute. I'm going to FOIL these two terms right here and see what we get. We have -4 times 5, so we have -20. Then we have plus 4r. Then we have minus 5r, and then plus r squared. Then we have this plus 18 still is equal to 0. We continue. This is quadratic in terms of r, so we have r squared. Then we have a minus r. And we have -20 plus 18 is -2. So we get to this point, and now we factor, or use the quadratic formula as appropriate. I think this one factors. We have r minus 2 times r plus 1 is equal to 0. And now we are able to continue to solve for r and get our two values. Now r will be 2. This is one eigenvalue, and r is -1. This is a second eigenvalue for this matrix. Now, a matrix of dimension 2, a square matrix of dimension 2, so a 2 by 2 square matrix, will have at most 2 distinct eigenvalues. I should also say, a 3 by 3, therefore, will have up to 3 distinct eigenvalues. It'll have no more eigenvalues than the dimensions of the matrix. That should be obvious because when we set up this equation, we wind up with a polynomial equation, effectively, of degree that matches the dimension. So this is a degree 2 polynomial that was created. This is a 2 by 2. And a degree 2 polynomial equation has at most 2 solutions. We'll have 2 solutions. Maybe some repeated, though. We'll have at most 2 distinct solutions. Now, -1 is one of our eigenvalues, which is not surprising because we saw up here that there exists non-zero r's and non-zero vectors x such that a times x equals -1 times x, where r is -1. So -1 is one of the eigenvalues for this particular matrix. 2 is the other. Now, to confirm with technology, okay, I do this using Wolfram Alpha. Type in eigenvalues of, and then notice how we can enter in a matrix. You enclose the entire matrix in brackets, and then you enter the matrix row by row using commas to separate the rows, and each row is in its own set of brackets. Just mind that notation. And then this confirms the matrix was entered correctly by saying that we're looking for the eigenvalues of the matrix -4, 6, -3, 5, and it gives us the 2 eigenvalues. The symbol there is a lambda. We're using r. It's very common to use lambda to represent eigenvalues, but there they are. 2 and -1 are the 2 eigenvalues. Okay, now each eigenvalue of a square matrix A has infinitely many corresponding eigenvectors, which are found by solving the matrix equation A minus Ri times the vector x is equal to 0. And we're solving this equation for the vector x. So we have to, for each eigenvalue, we have to repeat. So let's begin with eigenvalue equals -1. R is equal to -1 was our first, we'll call this R1, was our first eigenvalue. And we want to solve, we're going to solve A minus R1I times the vector x is equal to the 0 vector. This is what we're after. We're going to solve this. This is really just plug in -1 for R1. We get A plus I. So we want to add the identity matrix to this matrix right here. We're just doing A plus the identity matrix times x equals 0. And A plus I, we just have to add 1 to the main diagonal and see what this looks like. So we get -3 in the top left position. The entries on the not on the main diagonal don't change. And then add 1 to the other main diagonal, we get 6. And I'm going to do this by writing this system as an augmented matrix. So we have the equal sign next, and then we have the 0 vector on this side. And now we're going to put this in reduced row echelon form by using row operations. Okay, a few different row operations. I can see that the two rows are identical, so if I do -1 times the first row and add it to the second row, that'll zero out the second row. And then also I'm going to multiply the top row by -1/3 to get a +1 in that first position. So I'm going to do both of these row operations at the same time. We're in the same step, but not at the same time. Let's do this first row operation. So we do -1 times -3 and add it to 3. That gives me a 0 here. -1 times 6 and add it to 6 gives me a 0 here. And then -1 times 0 and add to 0, that stays 0. So we do 0 out the bottom row. And now the first row I'm going to rewrite after I multiply everything by -1/3. So we get a +1 here, a -2 here, and then a 0 there. Okay, this is in reduced row echelon form. Let's highlight the only leading one that we have here. Our solution will be of the form, I'm going to write this vector here as just xy. So we have the first column represents the coefficients of x, the second column represents the coefficients of y, and the y column has no leading one, so y is free. Then we simply translate or convert the rows into statements, into equations again. So we'd have 1x minus 2y is equal to 0. So x minus 2y is equal to 0. That comes from this first row. In other words, x has to be the same thing as 2y, and y is free. So our solution, because y is free, we're going to have infinitely many answers. Our solution has the form xy, where x is 2y, and y could be anything. So we can factor that y out, and we get 2, 1. Now this represents infinitely many answers, because y can be any variable. In fact, sometimes you will see a different letter introduced here instead of y, like a k or an s. But any multiple of 2, 1 will be an eigenvector corresponding to an eigenvalue of -1. Now, if we go back to our problem up here, notice that with -1 is an eigenvalue. If I use a vector 2, 1, then that is one of the corresponding eigenvectors associated with this eigenvalue. And sure enough, when I do a times x, I get -1 times x. Now, I can start right here with any multiple of 2, 1, because according to this, any multiple of 2, 1 is going to be an eigenvector associated with eigenvalue -1. So if I start up here with 4, 2 and multiply it to this matrix, you should get -1 times 4, 2. Or if I start with 6, 3 and multiply it to this matrix, I should get -1 times 6, 3. Any multiple of 2, 1, when multiplied to this matrix, will give you the -1 times that multiple of 2, 1. Okay, now let's shift focus to the second eigenvalue. The second eigenvalue is 2. So what we want to solve is a minus r2I times an x vector is equal to the 0 vector. And specifically, we're going to have a 2 in here for r2. So we have a minus 2I times the x vector is equal to the 0 vector. So we just have to remove 2 from the main diagonal here. And what matrix will this produce for us? Removing 2 from the main diagonal, I get -6, and then a 6, and then a 0, an augmented matrix, we'll have a 0 there. Remove 2 from the main diagonal, and to do the second row, remove 2 from the 5 position, so we have negative 3, 3. The other side of the augmented matrix, this side here is the 0 vector. And now we want to put this in reduced row echelon form. I can see that if I do negative 1/2 times the top row and add it to the bottom row, I'll zero out the bottom row, and then I'm going to multiply the top row by negative 1/6. And see what this produces for us. We should zero out the entire bottom row, and then multiply the top row by negative 1/6 will give me a 1, a negative 1, and a 0. Again, so this is in reduced row echelon form. There's the only leading one. It's in the x position, so once again we're going to say y is free, and turn that top row into an equation again, and it would read x minus y is equal to 0. In other words, x and y have to be the same. So our solution in this case will be of the form xy, where x has to also be y, and y is free, so you can factor the y out. And all vectors, all multiples of 1, 1, will be an eigenvector that corresponds to an eigenvalue of 2. Let's take the matrix A, negative 4, negative 3, 6, 5, and multiply it by any vector that's a multiple of 1, 1. So, I don't know, 3, 3, for example. Right? Picking any multiple of 1, 1 should be an eigenvector associated with the eigenvalue of 2. Now, according to what we found, it should be true that when I multiply this matrix and this vector, I should get twice the vector, because the eigenvalue is 2. Let's see if that happens. So we have these 3's going to multiply both those entries. So we have negative 12 plus 18 in the top entry, and then the 3's multiply to these entries, and they get added, and we have negative 9 plus 15. And let's see what this becomes. We get a 6 up top and a 6 down below. And notice we got twice the original vector. So when I did the matrix A times 3, 3, I wound up getting twice 3, 3. So 3, 3 is an eigenvector associated with eigenvalue 2 for this particular matrix A. Okay, now that we found the eigenvectors that correspond with these eigenvalues, let's use technology to confirm. I'm going to go back to Wolfram alpha, and we already have eigenvalues of the correct matrix entered, but notice that Wolfram alpha also gives you the corresponding eigenvectors, v1 and v2. v1 corresponding with the first eigenvalue and v2 corresponding to the second eigenvalue. And these confirm our answers. Also, Wolfram alpha is only giving you one example of an eigenvector. It's giving you the eigenvector that forms the basis for the rest of them. So when it says v1 equals 1, 1, you should interpret that as that's one example of an eigenvector, and that any multiple of this vector would also be an eigenvector. Okay, let's go on. The rest of this lecture is just practicing this. Find the eigenvalues and corresponding eigenvectors for the matrix below. All right, so we begin by setting up a determinant where all I do is I subtract r from both these entries, from the diagonal, from the main diagonal, and we're going to do a determinant. So I'm going to use an absolute value sign, as opposed to doing a bracket. And we have negative 1 minus r in the top left position, negative 1 over top right, bottom left is 1, and bottom right is negative 3 minus r. We want to find that determinant, set it equal to 0, and then solve for r. So we first begin, this is just a 2 by 2 determinant, so multiply those entries, and we have negative 1 minus r times negative 3 minus r, and then we subtract the product of these entries. So we do minus negative 1. So it's just going to be plus 1 is equal to 0. Now we do some foiling. We're going to have 3 plus r plus 3r plus r squared. All those negatives cancel each other. Plus 1 is equal to 0. This gives us r squared plus 4r plus 4 is equal to 0. And this gives us r plus 2 times itself is equal to 0. So in this case, we get two eigenvalues, but they're the same. So I'm going to write them as two separate things, even though they're the same value. We have a repeated eigenvalue of negative 2. Let's see what happens when I try to find the eigenvector. So we solve a minus r1i, so it's going to be a plus 2i is a matrix, times a vector. We want that to be equal to the 0 vector. Add 2 to the main diagonal, we get a 1, negative 3, 1, negative 1. So I added 2 to the main diagonal, and then we have equal to the 0 vector. So here's our augmented matrix, and we'll do row operations. There's only one row operation needed to be done here. -1 times the top row add to the bottom row will zero out the bottom row. And the top row does not need to be altered. It already has a 1 in the leading position. Okay, so once again we see that y will be free. We have only one leading 1 in the x column, so y is free. It can be any number it wants. And the first equation tells us that x minus y is equal to 0, so x has to be equal to y. So once again, our solution, similar to the previous matrix we just did, is of the form, or x is y, and y is free. Y could be anything. So any multiple of 1, 1. These are the eigenvectors. There's infinitely many. All multiples of 1, 1 correspond to the eigenvalue of -2. And that's all we can do for this one. Next example, find the eigenvalues and corresponding eigenvectors for the matrix below. Okay, once again, we begin by subtracting r from the main diagonal and doing a determinant. So we have the determinant 0 minus r is -r. The entries not on the main diagonal don't change. And then we have 2 minus r. Do that determinant, set it equal to 0, and solve for r. So this gives us -r times 2 minus r minus -2, so plus 2 is equal to 0. Distribute, we have -2r plus r squared plus 2 is equal to 0. This gives us r squared minus 2r plus 2 is equal to 0, and we need the quadratic formula to factor this, to solve this one. It does not factor, so we have r is equal to -b, so 2 plus or minus the square root of b squared minus 4ac. Well, b squared is 4, minus 4ac is going to be minus 8, all over 2a, all over 2. That's going to be an imaginary or complex, non-real valued eigenvalues, which can happen. And we have 4 minus 8 is -4, square root of that is 2i, and then you can divide everything by 2. And so we get our two eigenvalues are, first one is 1 plus I, and the second one is 1 minus I. Okay, now we want to look for the eigenvectors corresponding to each of these. And we can do this even though these are non-real valued. So let's begin with r1 equals 1 plus I. So I'm going to subtract 1 plus I from the main diagonal. And I'll skip a few steps here. Subtracting 1 plus I from the main diagonal gives us -1 minus I in that position, and then a 1, a -2, and then we do 2 minus 1 minus I, which will be 1 minus I. All right, our goal is to row reduce this. And to do this, I'm going to I like keeping the fact that this is already real valued down here at -2. I will do a row interchange to swap the two rows so that I have a real value in the top left position. And I'm going to also divide that entry by, so I'm going to do a couple things here. There's going to be a row interchange, as well as I want to do -1/2 of that bottom row, which will now be the top row. So we have a positive 1 here, and then we have a -1/2 plus 1/2 I, then our 0. And down below we have a -1 minus I, a 1, and a 0. Okay, now I'm going to use this leading 1 right here to zero out the entry below. In fact, it could be helpful to leave the -1/2 factored out. So this is -1/2 times 1 minus I. Okay, I'm going to multiply the top row by the opposite sign of this. So we're going to multiply the top row by 1 plus I, and then add that down to the bottom row. Okay, this will be some work that we have to do in our head here. So we do 1 plus I times 1. That's 1 plus I. Add that to -1 minus I, we zero out. Let me rewrite the top row real fast. We're not changing that. So we get a 0 here. Now I do 1 plus I times this term. Well, I'm going to do the 1 plus I times the 1 minus I. 1 plus I times 1 minus I. Let's just do that work on the side. We got 1 minus I plus I minus I squared. Well, the minus I plus I cancel. I squared is -1, so we get a 2 out of this. But then times -1/2. So we get a -1. Then add that to this one, and sure enough, we get a 0 here, and then we get a 0 in that position as well. Okay, we are now in reduced row echelon form. So we have a leading 1 here in the x column. Y, again, is free. Y is free because there's no leading 1 in the y column. And the first equation, the first row, yields the fact that, let me write it down below, yields the fact that x minus 1/2 1 minus I y is equal to 0. Okay, so that means that x is equal to 1/2 of 1 minus I y. So this gives that our solution to this is x and y, and x is 1/2 1 minus iy, and y is free. So there's our solution in form of xy, but written in terms of y. And we can factor out the y. And we have 1/2 1 minus I, and then 1. Now recall that y represents all possible constants. Y is free to be anything. So any multiple of this vector right here will be an eigenvector corresponding to this particular eigenvalue. And we can make this look a little bit cleaner if we want. We can go ahead and double both entries here. So it's just a simple 1 minus I 2, and then put any constant in front of that. So this family of vectors is the same as this family of vectors, because the y and the k just stand for any possible constant. And this eigenvector just looks a little bit cleaner as a basis for all the other eigenvectors. Okay, now let's go to the last eigenvalue for this. So R2 is equal to 1 minus I. And there's going to be a lot of similar work here, so let me move this over just slightly, maybe separate our work, and copy this, and we'll make some edits to it. And keep our work separate. There we go. Okay, what's going to be different? So this time I'm going to remove 1 minus I from the main diagonal. So removing parentheses 1 minus I is removing 1, adding I. So we're going to remove 1 and add I to the main diagonal. Remove 1 and add I, so this will be plus and this will be plus. That's all that's going to be different. I'm still going to do a row interchange and then do this, divide this row here by, or multiply this row by negative 1/2, so I'll still do that. And what will be different in this line here, this will be addition right there, and this will be addition right here. That's all that will be different. Now the row operation, I'm going to use this leading one right here to zero out this, so I want to multiply this by the opposite of this, so we need 1 minus I, not 1 plus I right there. Okay, that should accomplish our task. Let's verify. 1 minus I, we'll do 1 minus I times 1 is 1 minus I, then add it to negative 1 plus I gives me 0, check. And we're going to do 1 minus I times 1 plus I, and this should be a plus in my work right here. I need to make that change. So 1 minus I times 1 plus I will be 1 minus I squared, which is 1 plus 1, which is 2, times the negative half is negative 1, add to 1 is 0. So that still gives us 0. And of course, 0 times this is 0, add to 0 gives me this 0. So everything looks good here. All the edits are in place. X has a leading 1 in it. Y, the Y column does not, so Y is still free. And the first row would read that X minus 1 plus I, Y is equal to 0. So X is equal to 1/2 times 1 plus I times Y. So this should be a plus. This should be a plus, and then all the same reasoning as before. And we get all multiples of 1 plus I, 2, are going to be the eigenvectors corresponding to this eigenvalue, 1 minus I. And let's finish with a 3 by 3. Okay, to begin by finding the eigenvalues, we're going to have up to 3 distinct eigenvalues here because we have a 3 by 3 system, a 3 by 3 matrix. And that doesn't mean that all the eigenvalues will be distinct. Let's see what happens. So we're going to do a determinant and subtract r from the main diagonal. So let's switch to determinant notation, and we have 1 minus r, then negative 2, 0, negative 2, 1 minus r, 0, and then 0, 0, negative 1 minus r. Okay, so here we have a 3 by 3 determinant. We're going to set that equal to 0, and then solve for r and make this a true statement. And when you're doing the determinant of a 3 by 3, we want to do a cofactor expansion along a row or column that has the most zeros. So it doesn't really matter which one you pick. Let's pick this column over here. Let's get our matrix of signs correctly. So this is a plus. Always top left is plus, then minus, plus, minus, and then plus. So when I cross out this entry right here, which is the only one I'm going to have to cross out because zeros, the other entries in that column are 0, that we're in a positive position as far as the matrix of signs is concerned. So let's go ahead and let me put that plus in front. We do a positive of that, and we are going to focus on that but cross out its row and column. So we have a positive negative 1 minus r, so just a negative 1 minus r, times a 2 by 2 determinant of what is left in here, the black, not the orange. Don't change signs here. And so we have a 1 minus r, a negative 2, and a 1 minus r. And that's the only part we have to do on our cofactor expansion, because once again, those zeros will zero out. If these were non-zero, then you would have a few more terms that look similar to this that you would have to combine and simplify. Okay, from here, I'm going to just go ahead and factor a -1 out of this, so we have just 1 plus r, and then do our 2 by 2 determinant. So we have 1 minus r times 1 minus r. So we have 1 minus r squared. Then we have minus -2 times -2 is 4, so we just have minus 4. Now this is already partially factored, so I only want to really expand this, maybe this part here, and refactor it. I don't want to distribute this part through because it's already partially factored. So let's just leave that. You can put the r first if you want, -r plus 1, and then inside these parentheses we're going to get, and that is a square there, didn't look like it, but there we are. We're going to get r squared minus 2r plus 1, and then we have the minus 4 next. So this gives us r squared minus 2r minus 3. And then keep factoring and see what happens. -r plus 1. Here we have r squared. This is going to be r minus 3r plus 1. And we can see our solution from here. Our r values. R1, let's go with the single. R1 is 3. And then R2 is -1, and so is R3. So we have a repeated eigenvalue here. We have 2 distinct eigenvalues, but 3 total eigenvalues. Remember, we say that the multiplicity of -1 is 2, meaning it showed up twice as a solution. Okay, so there's the first part. Now we have to do some row operations for each eigenvalue. Let's start with eigenvalue 3, the one that was distinct. I'm going to rewrite this matrix here and subtract 3 from the main diagonal. So subtracting 3 from those 1s, look at those first. Those are all going to be, well, subtract 3 from 1 is -2. The middle one is -2, and the bottom right position is already a -1. Remove 3 from that will be -4. And the other entries don't change. And then we have this matrix times a vector x set equal to the 0 vector. So now we have an augmented matrix to solve this system. Okay, we're trying to get reduced row echelon form here. So I'm going to use, notice the first and second rows are the same. So I'm going to do -1 times row 1 and add it to row 2. That will zero out row 2. And also I'm going to multiply row 1 by -0.5. And I'm going to multiply row 4 by -1/4. So I'm going to do several things here in one step. Okay, let's do this row operation first. That zeroes out. Let's see, all these rows are going to change, so I don't know why I'm copying and pasting this, because, well, that zeroes out the middle row. The top row, we then multiplied everything by -0.5, so these will become +1s. And the bottom row I multiplied by -1/4, so that'll become just a 1. Okay, and just like that, we are in reduced row echelon form. There's 2 leading ones. Let's go ahead and emphasize them. There's a leading one here and a leading one down here. This one here is not a leading one because it's not the first non-zero entry in a row. Technically we're not in reduced row echelon form because I should do a row interchange of these bottom 2 rows. But this is okay. We can proceed without doing that. And so we have the x and the y is missing a leading 1 entry, so y again is free. And then of course the z column has a leading 1, so z is not free. Now we're going to turn the first and third rows into equations, and they look as follows. The first row would be x plus y, no z's, is equal to 0. In other words, x is equal to -y. This is what row 1 gave us. And then row 3 gives us simply that z is 0. So our solution, y is free, and x has to be -y, and z has to be 0. So x has to be -y, y is free, and z has to be 0. And if you factor out that y, you get all multiples of this vector, all multiples of -1, 1, 0, will be an eigenvector that corresponds to eigenvalue 3. Let's move that over just slightly. Separate this work. So you can guess now, if you were to take this vector and multiply it to this matrix, you should get 3 times the size of this vector. So I can predict right now that I'm going to get -3, 3, 0 when I do this. And you can start with any multiple of this vector. So what if I do twice that vector, make this -2, 2, 0, start with that, and take this matrix, multiply it by this vector. This is still an eigenvector associated with this eigenvalue. So when I multiply this vector to this matrix, I should get triple this vector. So I should get -6, 6, 0. I'll leave that to you to verify, to feel confident about what's going on here, what we're finding. Okay, and then we just have an r equals -1 to find the eigenvectors associated with this eigenvalue. Okay, so we're going to subtract -1 along the main diagonal. And subtracting -1 just means we're adding 1 to the main diagonal. So the main diagonal, let's write that part first. We're going to have a 2, and a 0. Adding 1 to every entry on the main diagonal. And all the other entries are the same. They don't change. And then augmented matrix, we have 0s there. Okay, so if I were to simply just multiply the top row by 1, don't change it. In other words, just add the top row to the second row to change the second row. This will put this, oh, and then I'm going to want to multiply the top row by a half next. And let's see what matrix we get. So the middle row should 0 out. Those should be all gone. Just add row 1 to row 2 in order to replace row 2. And then also I multiplied the top row by positive 1/2. So those will change to 1 and -1. Okay, so look for your leading ones. There's only one leading one in this at all. It's right there. And we have 2 rows of zeros. So that's x. Now, therefore, y is free, and so is z, because z does not have a leading one. So we have 2 free variables here. So our solution set to this will look like the following. Well, let's first translate row 1 into an equation. Row 1 translated into an equation would read x minus y is equal to 0, so x is equal to y. So x has to be y is free, and z is free. So we have 2 free variables involved here. We want to pull these apart in the following way. Anything associated with one of the free variables, write as one vector, and then anything associated with the other free variable, write as a separate vector. And then I can factor the y out of the first collection and then factor the z out of the second collection. And we see, okay, so here's how we can find any eigenvector associated with this eigenvalue of -1 was our eigenvalue. It's pretty much any multiple of 1, 1, 0 plus any multiple of 0, 0, 1. All right, so x, y, and z don't have to be the same. So one example of an eigenvector would be, let's triple the 1, 1, 0 and 5 times the 0, 0, 1, and then add them together. So I'll just really just put a 5 down here. In other words, we're doing this where y and z are whatever they want to be, and they're independent of each other. So you can choose y to be something and z to be something else entirely. So it should be that if I take this vector and I multiply it to this original matrix, I should get -1 times that vector. All right, so you take this vector times this matrix, you should get the opposite of this vector. So you should get -3, -3, 5 as a result. And I'll leave that to you to verify. Okay, and that wraps up this topic on what eigenvectors and eigenvalues are and how to find both of them.